Good afternoon, ladies and gentlemen. My name is Boutz. I'm a senior consultant at SGS Intron in the Netherlands, and today's presentation is on the aging coefficient of fly ash concrete. My co-authors are my colleague Gert van der Wegen and Angelo Sarabert from the Vliegersunie in the Netherlands, and the Vliegersunie is a fly ash supplier. My presentation has 4 sections. First, an introduction. Second, materials and methods. Then results and discussion. And I will end with conclusions. Nowadays, the required service life of reinforced concrete infrastructural objects like viaducts and tunnels equals 100 years or more. The main degradation mechanism of these structures is chloride-induced corrosion of the reinforcement. The service life of such chloride-loaded structures is determined by the chloride load, the thickness of the concrete cover, and the resistance of the concrete to chloride penetration. This resistance is inversely proportional to the chloride diffusion coefficient. The chloride diffusion coefficient is time-dependent, and the time dependency is described by the so-called aging coefficient N. Here we show this in this equation, where D0 is the diffusion coefficient at the reference time T0, which is usually 28 days. T is of course time, and N is the aging coefficient. In the Netherlands, we have used fly ash concrete with low Portland cement content and high fly ash content successfully on a large scale in the past 25 years, based on the equivalent concrete performance concept. However, it is well known that fly ash concrete has a high initial chloride diffusion coefficient, but shows a rapid decrease with time due to the pozzolanic reaction. Values of the aging coefficient reported in literature show a very large variation between 0.6 and 0.9, and such a variation has a very large impact on calculated surface life. Therefore, a long-term research program has been performed to examine the effect on the aging coefficient of different sources of fly ash and different origins and strength levels of Portland cement. In this program, we have used a reference concrete with blast furnace slag cement, which is the preferred choice in chloride-loaded environments in the Netherlands due to its high resistance to chloride penetration. All specimens were exposed outdoors, unsheltered, to stay close to practical conditions. Now let's take a look at the materials. We have used fly ashes from 3 different Dutch coal-fired power stations. The chemical composition is shown in the table here, and the chemical composition is fairly comparable. We have used 4 cements in this investigation. The reference cement is a blast furnace slag cement from a Dutch cement producer. And we have used 3 different Portland cement qualities, all in the strength class 52.5 normal, C1 from a Dutch cement producer, C2 from a Belgian cement producer, and C3 from a German cement producer. If we now take a look at the compressive strength development of the cement, as measured by the European standard 196-1, we can see that the reference concrete, the reference cement has the slowest strength development. C1 and C3, the 2 Portland cement qualities, have the highest strength development and are fairly comparable. And C2, the 3rd Portland cement quality, has the lowest strength development. For the investigation, we have used 6 different types of binder. One is the reference cement with SEM3B, and the other 5 are combinations with Portland cement and fly ash. The fly ash content is always 1/3 of the total weight of cement and fly ash. And in this table, we show the different combinations that we have investigated. By combining Portland cement C1 with the 3 different fly ash qualities, we can investigate the influence of the fly ash origin. And by combining fly ash 1 with the 3 different Portland cement qualities, we can investigate the influence of the Portland cement quality. If we now take a look at the concrete mixes, then in this table, the full concrete composition is shown. For all concrete mixes, the binder content was 360 kilograms per cube. And for the fly ash concrete mixes, the binder content is the total weight of cement and weight of fly ash. All concrete mixes had water binder ratio 0.45. We used river sand and gravel with the maximum grain size of 16 millimeters. And the fly ash content in the concrete mixes was 120 kilograms per cube, and the Portland cement content 240 kilograms per cube. Now let's take a look at the curing. The curing up to 91 days consisted of 3 steps, which had to assure that the fly ash concrete mixes show sufficient hardening under moist conditions. After casting, the mold was covered with a plastic foil and put in the climate cabinet at 95% relative humidity. After demolding, it was then stored in lime-saturated water up to 7 days. After 7 days, the cubes were wrapped in plastic foil and again stored in the climate cabinet at 95% relative humidity. And then finally, all specimens were unwrapped and stored outside under unsheltered conditions to be close to practice. Now let's take a look at the test program. First, we have the main program, which was performed on all 6 concrete mixes. We first measured the compressive strength development up to half a year. And then we measured the resistance to chloride penetration by the rapid chloride migration test following the anti-build 492. And this was done at 28 days up to 5 years. At the same time, we measured the electrical resistance by the 2 electrode methods. And this test has been performed on the RCM samples prior to testing RCM. So it was also performed between 28 days and 5 years. Then additional testing was performed on 2 concrete mixes, the reference concrete and 1 fly ash concrete mix at the age of 3 years. In this additional investigation, we have measured the chloride diffusivity following the European standards, the EN 12390-11. In this method, specimens are immersed in a sodium chloride solution during 90 days, after which a chloride profile is determined from grinding 1 millimeter thick layers. So now let's take a look at the results. First, in this slide, we show the development of compressive strengths for all 6 concrete mixes. If we then look at the fly ash mixes, we can see that all of these fly ash mixes show a slower strength development at the reference concrete, but reach similar strengths after half a year. And within the fly ash mixes, we can see that the strength development is mainly influenced by the Portland cement quality. Now let's take a look at the main results of the chloride migration coefficient, which is shown in this table for all testing times from 28 days up to 5 years. we then take a look at the results after 28 days, we see that all fly ash mixes show migration coefficients which are 1 order of magnitude higher than the reference concrete mix. But then, after 1 year, we see a rapid decrease of the migration coefficients to a comparable value as the reference concrete. And after 3 years, all fly ash mixes even show lower values. Then, after 5 years, the migration coefficients for the reference concretes remains constant, whereas that of the fly ash mixes seems to increase. However, we believe that this increase is an artifact by a change in test conditions. After 3 years, we are at the outer limit of the anti-build standard, where we have to apply the maximum voltage and maximum test duration, whereas after 5 years, the test duration was 1 step lower. We decided to rerun this test after 5 years for 2 of the fly ash mixes at the same test duration as after 3 years, namely 96 hours. And we see that now we obtain a test results which is comparable to the one after 3 years. So this is the result that we believe in after 5 years. Now let's take a look at the specific electrical resistivity. Here the results are shown for all of the concrete mixes. And we can see that there is a continuous increase with time for all of the mixes. And if we take a closer look at the fly ash mixes compared to the reference concrete, we see that up to 1 year, the electrical resistivity is lower for fly ash, but after 3 years, the resistivity is higher or comparable to that of the reference concrete. Now, it is well known that the TEM result and the RCM result show a good correlation. And also in our investigation, this is the case. In the diagram, we plot 1000 divided by the TEM value versus the RCM value. And we get a very good linear dependency. And the constant, which can be derived from this linear dependency, is shown here, which is quite comparable to literature values. Now, the main result of the investigation was to derive the aging coefficient of this long-term research program, and the results are shown in this slide. First, we see the diagram on a double log scale of the RCM value versus time for the reference concrete and for the fly ash concrete mixes. We can clearly see that the fly ash concrete has a very steep decrease of the RCM value. And if we now derive the aging coefficients from the slope of these curves, we see that the fly ash mixes have values between 0.8 and 0.95. And these values are much higher than that of the reference concrete. However, this result is somewhat troubled by the results after 5 years, which have proven difficult. So we have used a second method to determine the aging coefficient. For this method, we have used the K value from the linear relation between 1000 divided by 10 and the RCM value after 1 year. And we have calculated the RCM results after 3 and 5 years from that equation and combined that with the RCM values up to 1 year. If we then look at the aging coefficients derived by this method, we see that we have values of 0.7 up to 0.8. and that the 5 fly ash concrete mixes show quite comparable results. Then we have the additional investigation, in which we have used the natural diffusion method to determine the chloride diffusivity for the reference concrete mix and 1 fly ash mix. In this table, we show the results, and we can see that both concrete mixes have a chloride diffusivity of 0.7. It's almost identical, certainly if you take into account the standard deviation. Here in this diagram, the chloride profiles are shown. So it's quite a narrow depth of 7 millimeters. So the fly ash concrete mix has a almost identical diffusivity, and these values are in fairly good agreement with those of the RCM test after 3 years, which are shown here. So now I come to the conclusions of my presentation. First one is that the chloride migration coefficient of fly ash concrete is initially much higher than that of the reference mix with blast furnace slag cement, but that the fly ash concrete shows a very rapid decrease to similar values at 1 year and lower values at 3 years. That both the accelerated method and the non-accelerated immersion methods confirm that the chloride penetration resistance of fly ash concrete is equal or better than the reference concrete mix after 3 years. And that the quality of the fly ash has little or no effect on the aging coefficient. And finally, that the N value of fly ash concrete varies between 0.7 and 0.8 for fly ash concrete. And these values are in very good agreement with the National Dutch Guideline on service life calculation of reinforced concrete mixes. So I thank you for your attention, and I am available for questions.